Okay, so we were talking about individual atoms, which we find on the periodic table. However, most substances have more than one type of atom in them, so we call them compounds. So, let's talk about hydrogen, oxygen, and water. When two or more elements from the periodic table combine to form a compound, an entirely new substance results. So when you take hydrogen, which is a gas, you don't have to balance this equation yet, and you add it to oxygen, which is a gas, you get water, which is usually not a gas at room temperature. It's liquid. Water is nothing like oxygen gas and nothing like hydrogen gas. It's completely different. So it is a chemical change. When you take things from the periodic table and you smash them together, it is a chemical change. It is going to have different properties and everything. So here's a rundown of some things we're going to do in this chapter. We're going to talk about how to represent compounds, how to name compounds, that is important, how to name compounds is important. How to talk about different types of compounds, how to write equations, and how to calculate the composition of compounds. So notice I said calculation at the very end. So we're not going to be calculating for a while. I will tell you that moving forward, who's had chemistry before in high school that remembers a little bit? Okay. With some exceptions, most of this next unit that's on the next test, which is chapters 3, 4, and 5, will completely cover or go beyond everything you covered in high school chemistry, with some exceptions, but most of the time. So if it's all been familiar to you so far, excellent. If it has not been, we're about to sort of level the playing field maybe. But, all right, we'll move on. Chemical bonds. We'll talk about this in painstaking detail in April. Compounds, the atoms, they're held together. We call them bonds. That's what holds them together. Now, our chemical bonds come about from the attraction between the charged particles in an atom. What are our charged particles? Protons and electrons. Good. So it doesn't matter what order you put them in. Protons, electrons that compose the atoms. Because think about a magnet. If you have positive and negative charges, they are attracted to each other. And if they're the same, if you put a negative end of a magnet and a negative end together, they repel. So there's two types of chemical bonds that we're going to talk about. We're mostly just going to kind of mention them. Again, we'll talk about it in painstaking detail in chapters 9 and 10. But for now, two types of chemical bonds are ionic and covalent. They're right there. So for my visual people, I'll refer back to that. An ionic compound always has a metal in it. Where do we find metals on the periodic table? Yes, to the left of the stairs. So metals. They always have a metal. And if you remember the properties of metals lose one or more electrons to form what kind of ions? Positive ions, yes. So positive ions, which we call cations. So plus positive write it above it. And then it's going to have a nonmetal, so nonmetals here to the right of the stairs. Nonmetals gain electrons. So when you gain electrons, you form a negative ion, which is called an anion. So here we have one that's positive and one that's negative. So what's going to happen to them? They're going to attract. Yes, that is right. So they're going to attract. And this is a very strong attraction. And another way of saying this is in an ionic bond, the electrons are transferred. So if you like visual, here you have two atoms, so we'll say this is our metal and this is our non-metal. So the metal is going to lose this electron and it's going to give it to the non-metal. So that means this one becomes positively charged. This one is negatively charged. So they stick together like a magnet. So one electron is actually completely transferred to another. In a covalent bond, that's a little bit different. In a covalent bond, this happens when a nonmetal, so to the right of the stairs, forms a bond by sharing. So it shares an electron with another nonmetal. So this is two elements or more to the right of the stairs that are stuck together, and they are stuck together because they're sharing electrons. Now, the shared electron, so the one that where they're sharing them, is considered lower in energy. So it forms the bond. The bond is held together because these electrons that are shared, they're attracted to both nuclei. So they're attracted to the nucleus in both atoms. Sounds kind of weird. Let's look at it visually. Here's a covalent bond. So here's an atom. They're both nonmetals. So they're going to say, hey, I need an electron. I need one too. Let's play in the sandbox together and share. So they share. So when you share electrons, look, it's between them. See how both electrons are between the two atoms there? So neither of these electrons belongs to any one particular atom. They're shared. And so this electron is attracted to both the nucleus in both atoms, as is this one. Does that make sense? Good. Turn the page. Now, how we can represent a compound with several options. So we'll talk about the information that's given in each type of formula because it tells us different things, and depending on what we want to know, we'll write it a certain way. So an empirical formula, we'll calculate these later, it tells us the relative number of atoms. So it's a ratio. So for example, hydrogen peroxide has two oxygens and two hydrogens. So for every one hydrogen, how many oxygens are there? One. So one hydrogen, one oxygen. So the empirical formula for hydrogen peroxide that's going to be our example. We'll go for it. Hydrogen peroxide is HO. So that tells you every one hydrogen, there's one oxygen. If you like ratios or fractions, that will make a lot more sense to you. The molecular formula, which is what most people are most familiar with, it's going to tell you the actual number of atoms in the compound. So we'll say of each element. We'll be specific there. So hydrogen peroxide is actually H2O2. But you can reduce that down to a ratio, which is the empirical formula. Now the structural formula, again, we'll cover this in a lot of detail later, but we'll at least introduce it to you. It uses lines to show how the atoms are connected to each other. So if we want to write a structural formula for hydrogen peroxide, again, we're going to write, and there is absolutely no reason that you would need to know that right now as to why it's that way. That's just how it is. So this is what a structural formula, and so you can do more with the structural formula. You can see whether bonds are double bonds, triple bonds, single bonds. It's good. You'll talk about bond strength, bond angles, shapes, all later. So here, let's practice. We're going to write the empirical formulas. I'm giving you a molecular formula. So here we're trying to reduce this as much as possible if we can. So C5H12, can we reduce that to something that has whole numbers? Do 5 and 12 have a common denominator? No. So sometimes you can't. So that's as simple as it gets. So it's the same. How about with Hg2Cl2? Can we break that down further? Yeah, they both have a 2 in them. So HgCl would be the empirical formula that goes along with that. And then, I don't remember what that is. C2H4O2. Oh, it's acetone. All right, sorry, that's not necessary. Can we reduce this? Yes. So we reduce it to CH2O. Anybody totally lost? You're probably thinking this is pointless. It's not pointless. We'll come back to it. Now, you can use molecular models. These are actually 3D. We'll do this a little bit later. Most commonly, you'll use a ball and stick model. If you're going to have to go onto organic, you'll be working with models frequently. But what you can also do is these, where it eliminates the sticks, and so that's called a space filling. This is the most common one that we use. This is more closely related to reality, but it still works. This is a water molecule, in case it matters. Not right now. Questions? All right, let's turn the page.